Hello everyone, in this video I would like to tell you how to simulate some phenomenon, some kind of problem where we have to deal with surface Plasmon-polaritons. And we are going to do this task by means of 5 different time domain method. This is our well-known numerical method. And we can entitle this video like how to study surface Plasmon-polariton. Traveling wave by means of five different time domain method. Okay, the phenomenon that we are going to study along this video is the following. We have an electromagnetic field, this is the wave vector K, that impinge an interface between two media. This is an electric medium and a metal. We can use this reference system that acts and orthogonal to the blackboard plane. We have the wave axis. So we can imagine that the electric field have this direction, and this could be the magnetic field. This is a structure of a plane wave. This kind of structure, we have a transversal magnetic field mode just on the interface. It is very important in order to propagate this kind of wave, this kind of surface Plasmon-polaritons. The behavior, of course, the penetration into the metal is less than in the dielectric. This is the reason for this asymmetry with respect to the interface. We can achieve this kind of behavior because at the end it is not a real wave, it is an evanescence wave along the propagation of the energy on the interface. This amplitude go down, decrease its value as an exponential function, right? But the main goal of this video is to determine the condition on the mesh. This where mesh size of the computational domain in 5 different time domains. Usually, the Nyquist-Shannon theorem improves the size of this mesh. We have the Nyquist-Shannon theorem. If we want to sample a signal, electromagnetic signal properly, we have to divide the computational domain, the biggest element. This delta is the biggest element of this mesh in the computational domain must be smaller or equal than the wavelength, the half of the wavelength of the electromagnetic field. So this condition is different when we have a surface Plasmon-polariton traveling wave, because the wavelength of the surface Plasmon-polaritons is smaller than the electromagnetic field. So this parameter determines the mesh size, this value. In other words, we can rewrite, yes, surface Plasmon-polariton. This is the conditions in order to mesh the computational domain properly and to be in agreement with the Nigui-Shannon theorem. But the question is, what is the value of this parameter? We can consider that the goal of this video is to determine just this, the value of the wavelength of the surface Plasmon-polariton traveling wave. Okay, if you are watching this video at this point, it is because you know very well the Maxwell equation. So I'm not going to tell anything about, and I'm going to begin my explanation just on the Maxwell equation. We want to determine this parameter. We'll start writing the Gauss law for the electric field. This is the displacement electric vector. This is the intensity of magnetic vector equals 0. There is a magnetic charge, and the rotational, the curve of the electric field is equal minus change of displacement vector, intensity of magnetic vector with respect to time. This is the Faraday law. The curve of the magnetic field is equal to G current plus the partial derivative of the displacement electric vector with respect to time. This is the Ampere's-Maxwell law. Okay. Now we are going to impose some condition on this equation. With this, we create a framework where it is quite possible in some very important applications, some kind of problem that we can deal with. We find these conditions, and that's the reason because I'm going to use them. One of them, the first one, is that there is a charge, the free current of charge in the interface, and also there is a current. So we have one condition in this and in this equation. The second condition is about the medium. The constitutive equation, the displacement electric vector is equal to the electric permittivity multiplied by the electric field, and the intensity of magnetic field is equal to the magnetic permeability multiplied by the magnetic field. We suppose that we have isotropic and homogeneous media, and in the case of the two sides of the interface, we have a relative magnetic permeability equal 1. This is equal 1 in both sides of the interface. This allows us to write this parameter like the piping, mu 0. And this is equal to epsilon 0 multiplied by the relative electric permittivity. But there is something more. We have a zero space variation of the electric permittivity. It means that these parameters have the same value everywhere. And of course, we have two different values in both sides of the interface, but we will treat this discontinuity in this parameter by using boundary conditions. The first condition, it is not really a condition, it is only a form of writing this equation. We want to use only two terms, the magnetic and electric field. And we're going to remove the displacement electric vector and the intensity of magnetic field in this equation. So we can remove already these terms. Okay. We can write H in 0 H at 0 epsilon R E electric field, and we can write 0 and E. We can write 0 and E here because the displacement, the divergence of the displacement vector is equal to epsilon divergence of electric field plus electric field multiplied by the gradient epsilon. But we say that this is equal to 0 vector. So this scalar product is multiplied by a 0 vector. So this term is 0. We can, in that case, to write this equation. And in the same case with the magnetic field, because at the end this is a parameter, it's a number. Okay. Now, from these equations that we have to keep in mind along the process of calculation lambda as subscript pp, the wavelength surface Plasmon-polariton traveling wave, we are going to keep in mind these conditions. And now we apply the core operator in the Faraday equation at both sides of this equation. So we have this is equal minus 0 portion in time. Okay, we have a mathematical identity. I use vector A because it could be every kind of vector. It's equal to gradient of the divergence A minus Laplacian A. If we change this by the electric field, and using the Gauss law, this element is 0. So we can rewrite this equation like minus Laplacian of the electric field. This is equal to minus 0 multiplied by the partial derivative of this equation, the Ampere's law. So if we introduce this this right hand side of this equation just inside of this one, we have epsilon 0 epsilon r, second derivative of the electric field with relation to time. This is the wave equation for the electric field, right? This equation. Of course, we can rewrite this equation by using that c squared is 1 over epsilon 0 multiplied by mu 0. What else? Okay, we can suppose that electric field has dependence in time with a shape of harmonic signal. So we can rewrite the electric field in this form, G omega t. By doing the derivative this equation, we have and the second derivative using this here, we have minus omega squared. Okay. Now we have in this equation the following. However, omega is 2p nu, c is 1 nu, and we can write epsilon r 2p nu like nu squared. This is epsilon r multiplied by 2p, and square is epsilon r by y vector square. So we can replace this equation by this order. This equation is the Helmholtz equation. Sorry. This Helmholtz equation allows us to impose condition on this vector, the wave vector. But now we continue making suppositions, and we suppose a plane wave as impede the interface between dielectric and metal. This is the x direction, this is the back direction. And we can suppose, imagine, that the vector G is equal to ax or this plus R means metal or dielectric medium, right? Okay. The star, yes, so here is going to write this inside. This E0R. We suppose plane wave. This means that if we use this equation inside of the Helmholtz equation, we can transform this in the partial distribution of the electric field. In addition, we can determine the Laplace of this expression. It's equal, first derivative is minus gk, no minus, gk x r plus gk z r, because I make the first derivative, multiply everything, and the second derivative is the second is know about the second order, it's about the other variable, in this case set, and multiply for the vector A0 so this is the first derivative. The second will be multiplied this jg minus square, right? So we can write minus chi x r square plus chi z r square plus epsilon r k 0 square equals 0, because I have removed from the equation the electric field by simplifying. So we have the first condition. Kx r square plus kz r square is equal epsilon r k0 square. Okay. There is something evident, quite easy to see. If I have an interface and this is kx dielectric and this vector is chi x metal, this vector must be the same. So kx d, because they are tangential and they must be continual along the interface, in that case they must to have the same value. Right. Another condition. The second condition is given by the Gauss law. We know, one second please. We know from the Gauss law this is equal to 0. This means that epsilon r, epsilon 0. I'm going to use here the electric field. One 1 second. Because okay, I can use that this vector z minus omega t. But if I insert this, make the calculation, the divergence of this expression is okay, is g G okay, z r a z r multiply a g k x plus r k z r z minus omega t equals 0. I can simplify the star g. So I have at the end chi x r e x r plus a sub r k sub r equals 0. This is other condition. So I can rewrite this. That's right. Other boundary condition is the continuity in the normal direction to the interface of the dielectric electric field. It means the interface dielectric metal is the normal vector equal z. We have the vector in the dielectric and the Plasmon electric vector in the metal. This vector must to be in agreement with this boundary condition. The metal minus the dielectric equal the charge between the interface. So in the beginning of this calculation, we say that there is a charge in the interface. This value is 0. So we can rewrite this in terms of epsilon 0, epsilon r. This case no r, it's metal. A z metal that minus epsilon 0, epsilon dielectric, a z dielectric equals 0. So we have simplified another equation. Epsilon m a z on epsilon g a z t equals 0. The last equation is given by the tangent flow continuity. We know, the normal vector person actually multiplied by the electric field in the dielectric minus metal must be equal 0. So G, K can do this calculation. Z dielectric minus E Z metal. This is factor 0, and this is G if this must be the factor 0, just because this difference must be 0. So Ex m minus Ex t equal, they must be equal. Yeah? They must be equal. We have then group of conditions. We have two equations here. One equation, another equation. Right. Okay, and one conditions. We have. Now I'm going to rewrite this in material form. This is X dielectric, X metal, Z dielectric, Z metal equal 0, 0, 0, 0. So the first equation is 1. I have D, 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 and G. So I can write this like K X T 0 K Z D 0. Now I'm going to change this metal, 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 metal. I have 0 K S metal 0 K Z metal. This equation will be write like 0, 0 minus epsilon dielectric, epsilon substrate metal. And the last equation, this is epsilon minus 1, 1, 0, 0. It is something more. If I apply this and I call this simply isostrict X, I can remove this and this. Okay? If there is a solution for this equation, it is evident that the determinant of this system must vanish. So I'm going to calculate this determinant. I have Kx, but multiply this. This Kx 0, K 0, 0 minus x, minus epsilon g plus epsilon m 1, 0, 0. Minus, however, this 1 over 4 is plus, this plus. Minus, minus, plus. Multiply. So I have here, I'm going to put this dielectric X. Okay, plus 0 k z t 0 kx 0 k z m 0 minus epsilon g epsilon m. Okay. Now I can do this calculation. This is 0 0 0 0 kx epsilon g k z m plus 0 0 0 0 0 kx kz t epsilon m minus. So if I compare this, I have this relation. So if mass this must be zero, the determinant must vanish. So this value cannot be zero. In that case, we don't have a proper resolution. In that case, this must be zero. So the condition now is going to write it as here. Epsilon g k m z m minus epsilon m equal k z d. Okay. From the Helmholtz equation, I have shift this relation for the vector y vector. So I can write this k z dielectric square is equal epsilon dielectric k0 square minus kx square, because the dielectric and the metal in the x direction is equal, right? So can remove this. In the same case, kz metal is equal epsilon metal k0 square minus kx square. Okay. If we use this equation into this relation, g square, we have km square epsilon m k c square minus kx square equal epsilon metal square multiplied by epsilon dielectric that square k0 square minus kx square. So I can rewrite kx square multiplied by epsilon m square minus epsilon t square is equal to this left hand side of the equation and move at the right hand side of the equation. So here I have k0 square multiplied by epsilon m square epsilon t multiplied minus epsilon d square by epsilon m. Okay. Now I can remove this and say that kx is equal to the root square of k0 square multiplied by epsilon m square epsilon g minus epsilon m epsilon d square divided by epsilon m minus epsilon d square. Okay, however, usually the electric permittivity of another electric media is a real number, but the electric permittivity of the metal could be a complex number. This is a complex number. So if I want to know the wavelength of a surface Plasmon-polariton, this is let me think, to pick the real part of the kx. So how to simplify this expression? We can write xm x dielectric by xm minus xd. And this term can be written like m minus xg by xm plus xg. You can remove this with this, and then we can write that lambda surface Plasmon-polariton is equal to p over k0, the real part of epsilon m epsilon t epsilon m plus epsilon d 1/2. I'm going to rewrite this. Well, there is now clear conditions delta x, delta y, and delta z in the 5 different time domain must be the biggest of this parameter of this mesh size must be smaller than the wavelength, the half of the wavelength. That in this case is given by this expression. This is all, and thank you for watching this video, and I see you in the next one. Bye bye.